in the last lecture we found that if A is a matrix which we treat, it may be a real matrix, but we still treat it as a complex matrix. Suppose A is in C and N, then the characteristic polynomial C A lambda is a polynomial, is a monic polynomial of degree n with coefficients in C, and it is defined to be the determinant of lambda I minus A, and the eigenvalues of A, which now are allowed to be complex also, are precisely the roots of this polynomial, C A lambda. We again recall that if A is a real matrix, then the complex roots of C A lambda must occur in conjugate pairs. And since C A lambda is a polynomial of degree n, then the fundamental theorem of algebra gave us that the fundamental theorem of algebra gives us that C A lambda will have n roots in C, some of them may be repeated, may or may not be, but the repetition is allowed, some of them may be repeated. So, suppose there are k distinct roots, suppose lambda 1, lambda 2, lambda k are the distinct roots of C A lambda, with lambda 1 repeating A 1 times, lambda 2 repeating A 2 times, and so on, lambda k repeating A k times. What does this mean? This means the polynomial C A lambda can now be factored as the root lambda 1 appearing A 1 times. So, lambda minus lambda 1 to the power of A 1 is a factor, lambda minus lambda 2 to the power of A 2 is a factor, lambda minus lambda k to the power of A k is a factor. And this exhausts all the factors, because lambda 1, lambda 2, lambda k are the only roots, and since the polynomial of degree n will have n roots, we will have A 1 plus A 2 plus A k is equal to n, and since lambda 1 is a root, lambda minus lambda 1 must be a factor of C A lambda. So, A 1 must be greater than or equal to 1, A 2 must be greater than or equal to 1, A k must be greater than or equal to 1. Therefore, if the lambda 1, lambda 2, lambda k are the distinct roots and their multiplicities are A 1, A 2, A k, or the repetitions are A 1, A 2, A k, then the characteristic polynomial has the standard factorization, and these lambda 1, lambda 2, lambda k are now the distinct eigenvalues, they are the distinct eigenvalues of A, and their repetitions are called the algebraic multiplicities of these eigenvalues. A1, A2, AK are called the algebraic multiplicities. That is, the multiplicities as a root of the polynomial, algebraic multiplicities of lambda 1, lambda 2, lambda k respectively. Okay. So, therefore, given the matrix A, we have our complete picture of these eigenvalues. We first construct the characteristic polynomial, then we find the distinct roots, then we find their multiplicities, then we have all the eigenvalues. Lambda 1 will be an eigenvalue occurring A1 times, lambda 2 will be an eigenvalue occurring A2 times, lambda k will be an eigenvalue occurring AK times. A1 plus A2 plus AK will be n, and each one of these j's are greater than or equal to 1. So, this is the standard structure of the characteristic polynomial that we will from now on consider. So, we will follow the notation that whenever we write C A lambda in this form, we really mean that these are lambda 1, lambda 2, lambda k are distinct, and these A's are their multiplicities, and so on and so forth. So, this is the standard notation that we will follow from now on. Let us look at some simple examples. These are the same examples that we have seen before. In this context, we will now again look at it. Let us take the matrix A to be 1 minus 3 2 minus 2 0 2 1 minus 1 2. In the last lecture, we found that C A lambda is lambda minus 4 into lambda minus 2 into lambda plus 2. So, what are the eigenvalues here? Lambda 1 equal to 4, lambda 2 equal to 2, lambda 3 equal to minus 2, and the multiplicity of 4 is 1, because the power lambda minus 4 to the power of 1 is the factorization. Similarly, the algebraic multiplicity of lambda 2 is 1, and the algebraic multiplicity of lambda 3 is 1. So, the distinct eigenvalues are 4, 2, minus 2. So, the distinct eigenvalues of A are 4, 2, minus 2, each having algebraic multiplicity 1, each having algebraic multiplicity. From now on, we will write AM for algebraic multiplicity. So, each has algebraic multiplicity 1. Let us look at another example. A to be 3 minus 1 1 minus 1 3 1 0 0 4. In the last lecture again, we found that the characteristic polynomial was lambda minus 4 squared into lambda minus 2. Now, we find that there are two distinct eigenvalues, lambda 1 equal to 4 and lambda 2 equal to 2, and the multiplicity of the eigenvalue is 4 is 2, because we have lambda minus 4 to the power of 2, and the multiplicity of the eigenvalue lambda 2 is 1. So, thus we have two distinct eigenvalues here. One of them has algebraic multiplicity 2 and the other one has algebraic multiplicity 1. Let us look at another example, a simple example. A equal to 0 1 0 0. We treat all these as complex matrices, remember. In this case, we have the C A lambda, which is the determinant of lambda I minus A, which is lambda minus 1 0 lambda, which is lambda squared, and therefore, there is only one eigenvalue, lambda 1 is 0 and its multiplicity is 2. So, here is an example where we have only one eigenvalue and its multiplicity is 2. Algebraic multiplicity is 2. Another example, simple again, which we have seen before, 0 minus 1 1 0. We have characteristic polynomial, as we saw in the last lecture, is lambda squared plus 1, which can be factored as lambda plus I into lambda minus I. We find now, even though the matrix is real, we end up with complex roots. The two roots are the two eigenvalues I and minus I. Note that they are in conjugate pairs, because the matrix is real. Whenever the complex roots occur, they must occur in conjugate pairs, and the algebraic multiplicity of the eigenvalue I is 1 and eigenvalue minus I is 1. So, thus we have two complex roots with algebraic multiplicities 1 and 1 each. So, here note A is real, eigenvalue is complex, occur in conjugate pairs. So, the eigenvalues occur in conjugate. Whenever you have a matrix, real matrix, and it has a conjugate, it has an eigenvalue which is complex, the complex eigenvalues must always appear in conjugate pairs. So, now we have a fair idea of the eigenvalues. Remember, our search for the answer to the question about diagonalizability depended on finding these eigenpairs, n of them. Now, in the eigenpair, the pair, there are two things involved. The first part of the pair is a number, which is the eigenvalue. Now, we have seen the analysis of the eigenvalues. In order to search for these eigenvalues, you construct the characteristic polynomial, which is determinant of lambda I minus a. Then you go and find its roots, then including their multiplicities, they provide you with the n eigenvalues that you are seeking for. Maybe these eigenvalues are complex, and if the matrix is real, and if by chance it has complex eigenvalues, they will have to occur in conjugate pairs. So, now having got a fair idea of these eigenvalues, we will now go and look at what and where we should search for these eigenvectors. So, our next search or next analysis will be the eigenvector search. So, let us start with the matrix A, which may be real or complex. So, in general we will write as CNN. It could be real also, because any real matrix can be thought of as a complex matrix. So, consider a n by n matrix and look at its characteristic polynomial. As explained above, if lambda 1, lambda 2, lambda k are the distinct roots with algebraic multiplicities a 1, a 2, a k, then the characteristic polynomial can be factored at this. So, let the characteristic polynomial be this, where lambda 1, lambda 2, lambda k are the distinct eigenvalues. Now, with algebraic multiplicity, we will write A m for algebraic multiplicities respectively as A 1, A 2, A k. Now, our search for eigenvectors should be to find the eigenvectors for each one of these eigenvalues. So, now let us consider any one of them. So, let lambda j be one of the eigenvalues. Now, what does it mean to say that it is an eigenvalue? It means it should have a vector u associated with it, which is different from 0, such that a u is lambda j u. This means there exists u not equal to theta n such that a u equal to lambda j u. This is what is meant by saying that something is an eigenvalue, because it is an eigenvalue means determinant of lambda j minus a is 0. If the determinant is 0, lambda j minus a is not invertible, and therefore, this homogeneous system must have a non-trivial solution. All this we have discussed in the previous lecture. So, therefore, there is a vector u, it is different from 0 such that a u equal to lambda j u. This means the null space of A minus lambda j I, this matrix, A is an n by n matrix, I is an n by n matrix, and therefore, A minus lambda j I is an n by n matrix. The null space of this n by n matrix A minus lambda j I contains a non-zero vector u. This means this null space is non-trivial. Okay. So, let us denote by W j. So, let W j be the null space of A minus lambda j I. What does this mean? This consists of all those vectors in C n such that A x minus lambda j x equal to theta n. That is the set of all vectors in C n such that A x equal to lambda j x. And the important thing is that this W j has a non-zero vector u, and therefore, W j is non-trivial, dimension of W j will be greater than or equal to 1. W j is non-trivial because u not equal to theta n, u belongs to W j. The u that we observed here, there exists a u such that A u equal to lambda j u. Now, W j is non-trivial, and therefore, dimension of W j is greater than or equal to 1. This W j is called the eigenspace corresponding to the eigenvalue lambda j. So, W j is called the eigenspace corresponding to the eigenvalue lambda j. If you look at W j, it contains, because it is a subspace, the null space of any matrix is a subspace, and because it is a subspace it contains 0 vector, but we have seen that it contains vectors non-zero also. Every non-zero vector in W j is an eigenvector corresponding to W lambda j. Every non-zero vector in W j is an eigenvector corresponding to the eigenvalue lambda j. So, now we have for every eigenvalue a corresponding eigenspace called W j, and this eigenspace, every non-zero vector in this eigenspace is an eigenvector corresponding to W j, and the dimension of W j is called the geometric multiplicity of the eigenvalue lambda j, and is denoted by G j. So, G j is the dimension of W j. Now, since W j contains non-zero vector, we have observed above that the dimension of W j is greater than or equal to 1. So, G j is greater than or equal to 1 for every eigenvalue lambda j. we will denote the geometric multiplicity from now on as GM. So, AM will denote algebraic multiplicity, GM will mean geometric multiplicity. So, with every eigenvalue now we have two numbers, two integers, two positive integers associated. One is AJ, which is the algebraic multiplicity, it is the multiplicity as a root of the characteristic polynomial, and the Gj, which is the geometric multiplicity, which is the dimension of the eigenspace corresponding to the eigenvalue lambda j. So, therefore, if we have an eigenvalue lambda j, corresponding to that we have algebraic multiplicity Aj, corresponding to that we also have geometric multiplicity Gj. What we know is Aj is greater than or equal to 1, because it must appear at least once as a root of the characteristic polynomial. What we have observed now is Gj is greater than or equal to 1. What we also had was the sum of all these multiplicities as root must add up to n, A1 plus A2 plus Ak equal to n. We do not know whether G1 plus G2 plus Gk is equal to n. All we now know so far is that Gj's must be greater than or equal to n, greater than or equal to 1. Each one of them must be at least of dimension 1. Now, the question is, at the moment we will make a remark, we will prove this statement a little later, we need a little more material for that to be developed, but we shall now observe it can be shown at the moment. We will not try to prove it, we will prove it a little later. It can be shown that for every eigenvalue lambda j of A, the geometric multiplicity corresponding to lambda j, we know it is at least 1. We have just observed that Gj's are greater than or equal to 1. So, 1 is less than or equal to Gj, and this will be at most the algebraic multiplicity for j equal to 1 to k. We are assuming that lambda 1, lambda 2, lambda k are the distinct eigenvalues, A1, A2, Ak are their algebraic multiplicities, G1, G2, Gk are the geometric multiplicities. Then any eigenvalue, the geometric multiplicity is at least 1 and at most the algebraic multiplicity. At the moment we are not going to prove this statement. We know this part that 1 is less than or equal to Gj. The part that Gj must be less than or equal to Aj, we shall look at a proof little later. Let us now look at some examples. Take the matrix A, this is again we keep looking at the same examples which we seen before, minus 2 0 2 1 minus 1 3. Now, what is we have seen before that the characteristic polynomial is lambda minus 4 into lambda minus 2 into lambda plus 2, and therefore, there are 3 eigenvalues lambda 1 equal to 4 with algebraic multiplicity 1, lambda 2 equal to 2 with the algebraic multiplicity 1, lambda 3 is equal to minus 2 with algebraic multiplicity 1. These are the 3 distinct eigenvalues. Now, what are the eigenspaces? The first one W1 is the null space of A minus lambda 1 I, which is the null space of A minus 4 I. Now, let us find this out. So, what is A minus 4 I? A minus 4i from the matrix A in the diagonal we have to subtract minus 4. When we do that we get the matrix A minus 4i as minus 3, minus 3, 3, minus 2, minus 4, 2, 1, minus 1. That is, you take this matrix A and subtract 4 from the diagonals, because we are taking minus 4i. This diagonal will become minus 3, this diagonal will become 0, the third diagonal will become minus 1, 3, the third diagonal will become minus 1, okay, because we have to subtract 4 from it. And if we solve the null space A minus 4i x equal to theta 3, we get W 1 consists of all vectors of the form alpha into 1 0 1, such that alpha belongs to R. Therefore, 1 0 1 is a basis for W 1, and therefore, dimension of W 1 is 1, and that is what the geometric multiplicity is. So, the geometric multiplicity of this eigenvalue is 1, and note that G 1 must be at least 1, because we said j is greater than or equal to 1, and we also observed that G j cannot be more than A j. In this case A 1 is 1, so it cannot be more than 1, it cannot be less than 1, and therefore, it has turned out to be 1. Similarly, W 2 is the null space of A minus lambda 2 I, which is the null space of A minus 2 I. Now, again we have to subtract 2 from the diagonals, and so A minus 2 I, again you take the matrix A we had here and subtract 2 from the diagonal. This is the matrix A minus 2 I, you have to subtract 2 from the diagonal, you get the matrix 1 minus 1 minus 3 3 minus 2 minus 2 2 1 minus 1 1, and you solve the system now A minus 2 I x is equal to theta 3, where A minus 2 I is this, you get that W 2 consists of all vectors of the form beta into 0 1 1, where beta belongs to R. And therefore, 0 1 1 is a basis for W 2. Therefore, G 2, which is the dimension of W 2, is 1, because there is a basis consisting of exactly one vector. Finally, we find W 3, which is the null space of A plus 2 I, because it is A plus A minus lambda 3 I, lambda 3 is minus 2. So, we have A plus 2 I. So, A plus 2 I, again with the given matrix, it turns out to be you have to just add 2 to the diagonal, you get this matrix, and therefore, we want to solve A plus 2 I x is equal to theta 3, where A plus 2 I is this matrix, and when we solve this we get W 3 to be all the solutions are of the form gamma into 0 1 I am sorry 1 1 0, where gamma belongs to C or R. Since we are dealing with R, we can take it as real numbers also, and therefore, dimension of W 3 is 1, because 0 1 1 0 is a basis for W 3, and therefore, G 3 is equal to 1. So, in this case we have the eigenvalues 4, 2 and minus 2, their algebraic multiplicity is 1 1 1 and their geometric multiplicity is 1 1 1. So, 3 eigenvalues, each one of them has algebraic and geometric multiplicities equal to 1. Let us now look at another example. A 3 minus 1 1 minus 1 3 1 and 0 0 4. This is again a matrix which we considered in the last lecture, and we found that the characteristic polynomial was lambda minus 4 squared into lambda minus 2, and therefore, there are two distinct eigenvalues, lambda 1 equal to 4, lambda 2 equal to 2, with their algebraic multiplicities as 2 and 1 respectively. Lambda minus 4 whole squared, therefore, the algebraic multiplicity is 2. So, now let us find the eigenspaces. W 1 is the null space of A minus 4 I. So, you have to subtract 4 from the diagonal, and when you do that you get W 1. Okay, let us first write A minus 4 I. You subtract from the matrix A 4 along the diagonal. So, I get along the diagonal minus 1 and 0. So, the matrix becomes minus 1 minus 1 1 minus 1 minus 1 1 0 0 0, and then we find that W 1, if we solve A minus 4 I x equal to theta 3, which is a homogeneous equation which can be easily solved, we find that all the solutions can be expressed in the form alpha beta alpha plus beta, where alpha and beta belong to C. And now, we find that 1 0 1 and 0 1 1 is a basis for W 2 1. 1 0 1 is obtained by taking alpha equal to 1 and beta equal to 0. 0 1 1 is obtained by taking alpha equal to 0 and beta equal to 1. Since there is a basis consisting of 2 vectors, we have dimension of W 2 is 2, therefore, G 2 is G 1 is 2. The next eigenvalue, the next gives the next eigenspace. This is the null space of A minus lambda 2 I. Since lambda 2 is 2, this is the same as null space of A minus 2 I. Now, we have to subtract 2 from the diagonal. A minus 2 I is the matrix 1 minus 1 1 minus 1 1 1 0 0 2. Now, if we solve this, we easily see that the third equation gives x 3 equal to 0, then the first two give x 1 equal to x 2. So, therefore, if you solve this, we have to solve this, we get W to be the set of all vectors which are of the form beta into 1 1 0, the beta belongs to C. And therefore, 1 1 0 is a basis for W 2, and hence dimension of W 2 is 1, because we have a basis consisting of one vector, and therefore, G 2, which is the dimension of W 2, which is the geometric multiplicity of the eigenvalue lambda 2 is 1. So, in this case we have the two eigenvalues are 4 and 2, their algebraic multiplicities. The eigenvalue 4 has algebraic multiplicity 2, the eigenvalue 2 has algebraic multiplicity 1, the geometric multiplicities were again 2 and 1. So, we have this setup. Let us now look at one more simple example to illustrate what we are heading towards. Example, consider the matrix A 2 0 2 minus 1 3 1 minus 1 1 5. If we now find the characteristic polynomial, it is determinant of lambda I minus a, which is lambda minus 2 0 minus 2 1 lambda minus 3 minus 1 1 minus 1 lambda minus 5. When we expand this determinant, we get lambda minus 4 squared into lambda minus 1, lambda minus 1 whole square into lambda minus 2. Now, if you look at the eigenvalues, lambda 1 is 4, the multiplicity is 2, lambda 2 is 2 and the multiplicity is 1. The multiplicity is 2 here for lambda 1 equal to 4, because we have lambda minus 4 squared term. So, the root lambda equal to 4 appears twice, therefore, the algebraic multiplicity is 2. Now, let us again find the eigenspaces as before. W 1 will be the null space of A minus lambda 1 I, which is the null space of A minus 4 I. That now, what is A minus 4 I? We must remove 4 from the diagonal entries of the given matrix. The given matrix is here. So, if you subtract 4 from the diagonals change to minus 2, minus 1 and 1. So, we get A minus 4 I as minus 2, 0, 2, minus 1, minus 1, 1 and then minus 1, 1, 1. If we now solve the system A minus 4 I x equal to theta 3, we find that W 1 is, it consists of all vectors of the form, and therefore, 1 0 1 is a basis for W 1, and therefore, dimension of W 1 is 1 and therefore, G 1 is 1. The geometric multiplicity is the dimension of W 1 and therefore, it is equal to 1. Let us now find W 2, the null space, the eigenspace corresponding to the eigenvalue lambda 2, which is the null space of A minus lambda 2 I. Since lambda 2 is 2, this is null space of A minus 2 I. Now, I have to subtract, to find A minus 2 I have to subtract 2 from the diagonal of the given matrix. When I do that, I get this matrix, and then now we solve for the system A minus 2 I x equal to theta 3 to get W 2 as the set of all vectors of the form beta into 1 1 0, where beta can vary over the complex numbers. Now, 1 1 0 is a basis for W 2, therefore, dimension of W 2 is 1. That means, the geometric multiplicity is 1, because geometric multiplicity is the dimension of the null space. So, what do we have in this example? We have in this example the eigenvalues as 4 and 2. The two eigenvalues were 4 and 2. Their algebraic multiplicities were 2 and 1, and the geometric multiplicities were 1 and 1. Now, here is an example where one of the eigenvalues, namely the eigenvalue 4 has algebraic multiplicity 2, but a geometric multiplicity which is smaller than this. This is what we said, that we will always have the geometric multiplicity is either equal to the algebraic multiplicity or smaller than the algebraic multiplicity. In fact, the entire question of whether A is diagonalizable or not depends on whether the geometric multiplicity falls short at any stage. If it falls short of the algebraic multiplicity, we will end up with a difficulty about diagonalizability. In fact, if it falls short even for one eigenvalue, even by 1, suppose there are 4 eigenvalues, for 3 eigenvalues algebraic multiplicity is equal to geometric multiplicity, but for one of the eigenvalues the geometric multiplicity is just 1 less than the algebraic multiplicity, then diagonalization will fail. We will see these facts little later. So, this relationship between geometric multiplicity and algebraic multiplicity, we know that both are at least 1 and the geometric multiplicity is at most the algebraic multiplicity. It can never be more than. We have not proved it, we will prove it a little later. Now, there is one more property which we will state now, which we will not prove. Okay. We will again prove this later. Remark, suppose lambda 1, lambda 2, lambda r are distinct eigenvalues. Some of the, we may not take all of them, some of the distinct eigenvalues of A, and phi 1, phi 2, phi r are corresponding eigenvectors. What does that mean? This means phi j's are not 0 and A phi j is equal to lambda j phi j for j equal to 1 to r. So, we are considering some r distinct eigenvalues and we are looking at eigenvectors corresponding to them, then we can show, again at the moment we are not going to prove it, we shall prove it little later. We can show that phi 1, phi 2, phi r are linearly independent. What does that mean? It can be simply stated as eigenvectors corresponding to distinct eigenvalues are linearly independent. So, in short, what we are claiming is this: eigenvectors corresponding to distinct eigenvalues are linearly independent. Eigenvectors correspond to distinct eigenvalues are linearly independent. Now, this is what is going to help us to see whether we are going to have diagonalizability or not. So, now let us case the simplest case. Why? We will see why this is the simplest case. The simplest case is, so A is complex matrix, we have the characteristic polynomial lambda minus lambda 1 to the power of A 1, lambda minus lambda 2 to the power of A 2, lambda minus lambda k to the power of A k, with the usual notation that lambda 1, lambda 2, lambda k are the distinct eigenvalues, A 1, A 2, A k are the algebraic multiplicities, and then W j to be the eigenspace corresponding to the eigenvalue lambda j. What is this? This is nothing but the null space of the matrix A minus lambda j I. So, given the matrix A, we have these ingredients, and G j, the algebraic multiplicity the geometric multiplicity is just the dimension of W j. So, we know 1 less than or equal to G j less than or equal to A j. We have asserted, we have not yet proved it, but we say we will prove it later. The geometric multiplicity will be always less than or equal to G j. So, suppose G j is equal to A j for every eigenvalue lambda j. That is, the algebraic multiplicity is the same as the geometric multiplicity for every eigenvalue. Then we have therefore G 1 plus G 2 plus G k is the same as A 1 plus A 2 plus A k, but A 1 plus A 2 plus A k is we know is M. So, how does it help us? Okay. So, now let us look at this. We have this whole space V which is C n and the W j is sitting here. This is the subspace. Now, the dimension of this W j is equal to G j. What does that dimension of W j is equal to G j mean? The dimension of W j is equal to G j means that we can find a basis for W j consisting of G j vectors. Okay, so, let us first G j equal to dimension of W j, but we have assumed implies A j equal to dimension of W j, because we have assumed A j equal to G j for every lambda j. Since we have assumed that the geometric multiplicity is equal to the algebraic multiplicity for every eigenvalue, we have that the dimension of W j is A j. This means we can find a basis consisting of G j vectors, which is the same as A j vector, G j equal to A j, G j equal to A j vectors for W j. Say, let us call them as phi j 1, phi j 2, phi j G j. Now, the superscript the superscript j tells us that we are talking about the jth eigenspace, and the subscript tells you the eigenvalue eigenvector numbering, basis vectors numbering. There are A j vectors in the basis. So, there are 1, 2, 3 A j subscripts, and the superscript j says these are all basis vectors for W j. Now, we observe that every non-zero vector in W j is an eigenvector for A corresponding to the eigenvalue lambda j, and these phi 1, phi 2, phi A j are non-zero vectors because they form a basis, and therefore, they must be eigenvectors. These are all eigenvectors corresponding to the eigenvalue lambda j, and therefore, lambda j phi j 1 is an eigenpair, lambda j phi j 2 is an eigenpair, lambda j phi j A j is an eigenpair, gives us A j eigenpairs for A. So, therefore, the subspace W j, the eigenspace corresponding to lambda j, has already generated A j eigenpairs. Notice that the vectors phi 1, phi 2, phi j j appearing in this eigenpair are already linearly independent, because they are forming a basis for W j. Okay. Note, phi j 1 etcetera phi j a j are linearly independent. So, thus we have W j alone giving rise to A j eigenvectors. So, we have W 1 gives rise to A 1 eigenpairs, W 2 gives rise to A 2 eigenpairs, and so on. W k gives rise to A k eigenpairs. Now, the eigenvectors appearing in these eigenpairs are linearly independent, the eigenvectors appearing in these are linearly independent, the eigenvectors appearing in these are linearly independent, but we do not know whether the eigenvectors appearing in this and this together are linearly independent. Suppose they are, then we would have got A 1 plus A 2 plus A k, which is n eigenpairs, and we would have had diagonalizability. If we can show that, which we have already claimed that it is true as claimed before, that eigenvectors corresponding to distinct eigenvalues are linearly independent, then these will give us together, when I say these, I mean these will give us together A 1 plus A 2 plus A k equal to n eigenpairs in which all the eigenvectors involved are linearly independent, and thus we would have had n eigenpairs as we are looking for, and hence A will be diagonalizable. So, therefore, we have shown that if we can show that eigenvectors corresponding to distinct eigenvalues are linearly independent, number 1, and number 2, if we assume that the geometric multiplicity is equal to the algebraic multiplicity for every eigenvalue, then A is diagonalizable. So, let us what is the conclusion therefore? Let us summarize all our discussion. Conclusion. Suppose we have a matrix A for which the geometric multiplicity is equal to the algebraic multiplicity for every eigenvalue, implies A has n eigenpairs in which all eigenvectors are linearly independent, implies A is diagonalizable, but this was provided the following holds. Eigenvectors corresponding to distinct eigenvalues are linearly independent. So, this is an important property which we have to prove. If we can prove this property, then what we have observed is that if the geometric multiplicity is equal to the algebraic multiplicity for every eigenvalue, then the matrix is necessarily diagonalizable. Now, let us look at a very special case. So, before we do that, let us remember, therefore, this property that we have listed here is an important property which we have to prove, and we shall look at this property in the next lecture. But now let us look at a very special case. A very special case is A has n distinct eigenvalues, that is all the eigenvalues are distinct. So, A has n distinct eigenvalues, and in that case we have A equal to lambda minus lambda 1, lambda minus lambda 2 into lambda minus lambda n, and therefore, the algebraic multiplicity of lambda j is equal to 1, but since the geometric multiplicity has to be at least 1 and it cannot be more than geometric algebraic multiplicity, we also get this is equal to the geometric multiplicity of lambda j. And since A m equal to G m for every lambda j, we have A is diagonalizable. And therefore, a special case is that if a matrix A has n distinct n distinct eigenvalues, then the matrix A is necessarily diagonalizable. And as we observed, this is the crucial point that we have to now look at, whether the eigenvectors corresponding to distinct eigenvalues are linearly independent. If we can prove it, we have achieved a long goal, namely the cases where the geometric multiplicity is equal to the algebraic multiplicity for every eigenvalue, we are guaranteed the diagonalizability. We will further see details of this diagonalizability once this property is proved, and that will be the goal for our next lecture.